Let's continue on now looking at a combination circuit that combines both series and parallel elements. So here we have a circuit shown and we want to know the equivalent resistance. So what can we replace these 5 resistors with? One resistance that will be equivalent to this 5 resistance setup. And then specifically picking out R2 here and saying what is the current at R2 and what is the voltage drop at R2. Now that second part of that question seems quite a bit more difficult than it really is, so we'll take a look at how to do that right now. So let's look at, first of all, let's find how we would go about doing that. And remember, I told you that the best way or the easiest way to do that is to start out by picking out pieces that you can reduce. And here is a piece, R3 plus R4, which I will call R34, is a series of 3 and 4, so we can just add those two. And in this case, it's 5 plus 15, or 20 ohms. So now we have this is one resistance of 20 ohms, and it happens to be in parallel with R2. So the equivalent for R2, 3, 4, let's start out with 1 over that, is going to equal 1 over R2 plus 1 over R3, 4, which is going to equal 1 over 60 plus 1 over 20, which is going to equal, if 60 is our denominator, it's going to be 1 plus 3 is 4. So R234 is going to equal the inverse of this, or 15 ohms. The next step, now we've reduced all of this to one resistance, which is in series with these other two. So RE now is going to be the sum of R1 plus R234 plus R5. Which is going to equal 25 plus 15 plus 20, or 60. So the equivalent resistance is 60 ohms. Now, in order to do the next part of this, we have to take a look at we have to know the voltage that enters right here, because this combination with this is in parallel. So if we know the voltage coming in here, we know that the voltage passing through here is the same as the voltage passing through R2. Okay? So the voltage, and I'm going to call this voltage at 234, is equal to the resistance 234 that we just calculated times the current that enters here. So we'll call that 234. So how do we know the current that enters here? Well, this current is in series with these 3. So whatever the total current is also going to be the current that enters this point right here. And so the total current is going to be equal to the total voltage divided by the equivalent resistance that we just calculated, and that's going to be 120 divided by 60, or 2 amps. So the current 234 is the same as the current at 234, and so V234 is equal to R234, which we found was 15, times I234, which was 2, or 30 volts. So the voltage drop at R3 is going to be the same as the voltage drop that comes in here. So that's 30 volts. So that's your second answer. What is the current at R3? Well, the current at R3, or R2, excuse me, we've already really calculated that. That's going to equal 2 amps. That comes from this calculation over here. Now let's move on and talk about what's known as internal resistance. In order to do that, we have to understand that the voltage that a battery produces is not the same as what's called the electromotive force. The electromotive force is what's inside the battery when the current is not flowing. And that is a product or as a result of the chemical reactions that occur inside a battery that produces its electromotive force. Now, once it starts flowing, by the nature of all substances, there's a certain amount of internal resistance. The internal resistance is the resistance that's inherent to the source itself. In this case, it's shown as the battery. And what you can see, and the important part of this is over here on the other side, over here on the right is the formula that calculates the difference between the electromotive force and the actual voltage produced by the battery. And the electromotive force, or the voltage produced by the battery, is equal to its electromotive force minus the current times its internal resistance. And so there's a small amount of energy lost internally to a battery when it's being used. And in many cases, this is exactly why batteries become warm when they're being used. Now, the terminal voltage is the voltage across the terminals, okay? It makes sense. And the terminal voltage is, as we've said before, controlled by the combination of whatever the load is and whatever the internal resistance is. Now, when you put sources in together, there are many ways that you can arrange these sources. In this case, we've arranged two sources in series, and we have made it so that these two sources are in the same direction, so that the positive and the negative are both pointing up. Therefore, the flow is for both of these is in the same direction from the bottom to the top. So when you connect a series connection of two voltage sources, the EMFs, which are scripted E here, and the internal resistance, which are R subscript 1 and R subscript 2, both of these are summed together. The E1 and E2 are summed together, and R1 and R2 are summed together because they're both in series. Now, when you have a situation like this, it's interesting that these two oppose each other. If you look at the supply source on the left, its flow is going to come out the top and head across from left to right. If you look at the supply source on the right, its source is also going to come out the top and head the other direction right into the... So these two are actually hurting each other, and you can see by the formula that the combined actual EMF is going to be E1 minus E2. And again, the internal resistance will be divided into that to show the actual voltage. And so here's a situation where you have multiple voltage sources and a source, so that the current is going to equal to the sum of the two EMFs divided by the sum of the two internal resistances and whatever the load is. So let's take a look at a couple problems. And the first problem says you have a circuit that consists of an 18-volt battery with an internal resistance little r and a resistor or a load of big R. The terminal voltage, that is V, is equal to 15.8. So you see the difference in the EMF of the battery and the actual terminal voltage. And the rest is assumed to be lost to the internal resistance. The current's 4 amps. So what is the internal resistance of the battery, and what is the resistance R in the circuit? Well, let's take a look at how we would do this. First of all, we know that V is equal to E minus I little r. And we know that V is 15.8. We know that E is 18. And we know that I is equal to 4. So this is a pretty straightforward calculation. We know that 15.8 is equal to 18 minus 4 times little r. And if you do the math here, little r has to come out equal to 0.55 ohms. Now, how about the rest of it? Well, how about big R? Well, V is equal to I times the sum big R plus little r, because these two guys are in series. And so we know that 15.8 is going to equal 4 times big R plus 0.55. And again, if we do the math here, big R has to equal 4.5 ohms. So let's take a look at the second problem here. It's a little bit more complicated. Second problem says a battery has an EMF, script E, and an internal resistance R. When the battery is connected to 25 ohm resistance, so when big R is 25, then the current is equal to 0.75 amps. Okay. And when the battery is connected a second time to a different level of 53 ohms, then the current produced is 0.45 amps. So find the EMF of the battery and its internal resistance. Well, we know that V is equal to I times R plus little r. And we also know that V is equal to E minus IR. These are the two formulas we have to take a look at. So we know that V is going to equal 0.75 in this first setting times 25 plus little r. And then over here in this second setting, we know that V is equal to 0.45 times 53 plus little r. So that means that over here, this is 18.75 plus 0.75 little r. And then here, it's going to equal 23.85 plus 0.45 little r. Now obviously you can put these V's together, set this V is equal to this V, and solve for little r. And if you do that, little r actually comes out pretty big, 17 ohms. And if you put that in this formula here, that means that the voltage here is 31.5 volts. So what's the EMF here? Well, we know this formula, that 31.5 is going to equal E minus I, and you can pick either one of these, it doesn't matter which one. I just happen to pick the 0.75 times 17, so that E ends up equaling 44.25 volts. So in this case, the actual battery produces a considerable more voltage than is actually produced at the terminal because of the fairly high internal resistance of the battery. Now you would predict with this kind of internal resistance that you might see quite a bit more. So let's look at this problem. This problem says you have a circuit shown below in which the EMFs of each of these is 12 volts. The R in each of these is 3 ohms, and the internal resistance is 0.5. So that's for each of these 3 batteries. The internal resistance is 0.5. the load, all four of these loads, the external resistance is 3 each, and the EMFs is 12. So the question on this one is, what is the total voltage? Now that's not the total EMF, that's the total current, or the total terminal voltage. So first of all, we know that E is going to be equal to the sum of these three E's. And so that's going to equal 12 times plus 12 plus 12, or 36 volts. So that's the EMF. We also know that all these resistances are in series, so that the internal equivalent, you could call this equivalent, that's going to equal 3 times 4 is 12, plus 3 times 0.5, or 1.5. So the equivalent resistance here is 13.5 ohms. So that means that your V, which is equal to E minus I, R, well, you need to know I here. So I is going to be, so we know that V is going to equal 36 minus I times 1.5. We also know that I is going to equal whatever V is divided by 13.5. So we have two equations and two unknowns. So we can either way we can put these together, however you want to do that. We can say that 13.5 I is equal to 36 minus 1.5 I. And so that means that 15 I is equal to 36. So I is going to equal 2.67 amps. And then substitute that back up here. It's going to be 36 minus 2.67 times 1.5. So V is going to end up being approximately 32.